Hi, my name is Chichi Junior Wachiku, and this is Physics 2211 Lab 5, Choose Your Own Adventure, and I chose to the following Slinky. Okay, here's our table of contents. First, we're going to start with an introduction, then we're going to go to fundamental principles, then to tracker analysis, then to data analysis and conclusions, possible errors, and then further questions. Okay. The purpose of this lab is to predict the motion of a falling slinky and analyze the effects of its surroundings. Gravity and drag will be calculated to determine their effect on the slinky's position. The system will be the slinky and the surroundings are the Earth. The observed position will be calculated using tracker, and the predicted position will be calculated using glow script. As a result, or like a brief preview of the result, is that although there are some fluctuations, the body's slinky will remain stationary. Here's some fundamental principles that we'll need for the lab. Newton's second law, the momentum principle. A system's change in momentum is proportional to the net force applied. Drag force, which is the resistance force caused by the motion of a body through a fluid, such as air. And then like the gravitational / like the force of the slinky. The slinky is like the tension force and is opposite to the gravitational force. Here's some formulas. We have the velocity update formula, which is Vf equals Vi plus F net over m times delta t. And then the position update formula, which is the final position equals the initial position plus the average velocity times the change in time. And then Newton's second law, which is the net force is equal to the momentum, or the change in momentum over the change in time. From Newton's second law, we can also derive that the final momentum is equal to the initial momentum plus the net force times the change in time. Okay, here's our tracker analysis. I'll let that play one more time while explaining the initial conditions. Actually, sorry. Okay. The initial conditions, the mass of the slinky is 0.218 kilograms. The initial position is 2.207 times 10 to the negative 2 in the x component, negative 1.264 in the y component, and 0 in the z component. The initial velocity is 0 meters per second. I forgot to put the positions in meters, and the initial height is 1.7 meters. Okay, and now for our computational model. Okay. So we have the mass of the ball here, the position, the velocity, the initial time, so 0, and the change in time here. Gravity, and those are all our initial conditions, really. Force of gravity, the force of the slinky, the net force, which is the force of gravity plus the force of the slinky. Then you have the velocity update formula here, the position update formula here. All right, and then our while loop here. And you do the force of gravity again. And yeah. Here are our results and possible errors. Here's a graph you can see between the observed and predicted. The red line is the predicted, and the observed is the blue line. The possible error number 1 is observed motion experiences fluctuations due to external forces not accounted for by the model. Possible error number 2 is the inaccurate tracking point placement on tracker, which is just like human error. And any further questions? Why does the bottom of the slinky remain stationary? The forces in the y direction cancel out. Although the gravitational force acts downward, the slinky acts as a brake spring and counteracts the force with a tension force of equal and opposite magnitude. What if we put a large weight at the bottom? Would it remain stationary? It depends. As long as we have a slinky that is either long enough or has a large enough spring constant so that the tension is equal to gravitational force, The weight will remain stationary until the top of the spring reaches it. All right, that's it. Thank you.